In the last video, we took a look at how we could justify Green's theorem through a partial proof. And in this video, we're going to try to take a look at some notation surrounding Green's theorem, as well as how we can actually apply this to a specific example, in example number 2. First, I want to refresh on what exactly Green's theorem told us from the last video. Green's theorem said that if C was a positively oriented, piecewise smooth, simple, closed curve, it closes in a region D. It's bounded by that curve. If it's the case that I have a line integral over here where P and Q represent functions that have continuous partial derivatives, then instead of computing this line integral, I can compute this double integral and get the same result. Okay, so let's take a look down here after our proof to see some important notation. So first off here, we're going to see that sometimes the notation here with an integral symbol and my curve at the bottom and this kind of regular old line integral or work integral setup will be used, but I'll have this extra little circle. By having that extra little circle notation, that's sometimes used to indicate that the line integral is calculated using specifically a positive orientation. So when you see that little circle, we're saying C is positively oriented. Some other notation is that for a positively oriented boundary curve of D is often sometimes referred to as this kind of partial D symbol that we have listed here. So when I am dealing with this symbol down here, notice I'm substituting that in place of C because this is saying the boundary of the region D. So that kind of partial here is oftentimes used to help indicate a boundary. We'll see that coming up in some of the future sections as well. Well, let's take a look here to see how we can apply Green's theorem to a specific example here in number 2. I want to go ahead and evaluate this line integral, where C is the triangular curve consisting of line segments from 0, 0 to 1, 0 to 1, 1, or to 1, 0 to 0, 1, on and on and on. Okay, well let's see what we can actually come up with here. I'm going to go ahead and quickly sketch out a nice XY axis. Okay, I'm going to put that over here on the side. And let's take a look at what exactly we can do with this once we have it. All right, so I want to go ahead and try to sketch out my region D and my curve C. So let's see. I know that I'm starting here at 0, 0. I'm going to go out to 1, 0. I also have, okay, so I'm going this way, 0, 0 to 1, 0. I go from 1, 0 to 0, 1. So that's up here. I go this way. And then I go from 0, 1 back to 0, 0. Okay, so there's my curve C, and I can see D is the region enclosed on the inside. So this is what I'm working with. So if I wanted to go ahead and try to apply Green's theorem, I'm going to first have to notice some of the initial setup with Green's theorem. Notice I have Green's theorem listed here. Notice that the function in front of the dx is my p, and the function in front of my dy is my q. So I can see down here that x to the 4th is p, and xy is playing the role of q. So I'm going to go ahead and write this. So first I'll say, we see that p of xy is really here just equal to x to the 4th, and q of xy is equal to x times y. Okay. I'm going to go ahead and check all the conditions of Green's theorem just to make sure that I can actually use it. So I'll start by saying we note that C is, well, it is positively oriented. It is piecewise smooth. It is simple, and it is closed. So it checks off all those particular boxes. I also can check here that definitely P and Q, since they're both polynomial functions of two variables, then they are definitely going to have continuous first-order partials. So P and Q here will certainly have continuous first order partials. Okay. Specifically, they'll have those throughout all of R2, and so, well, maybe not so. And R2 contains the region D. Notice that those were all the conditions. I needed to have a positively oriented, piecewise smooth, simple closed curve, and I also need to have P and Q with continuous first order partials in a region that contained D, and they definitely work in the region of R2. Okay, so now I can go ahead and using Green's theorem, I can kind of apply that. If I wanted to compute this work integral that I have up here, I can instead compute this double integral. So, by Green's theorem, my integral along C, x to the fourth dx plus xy dy is automatically going to be equal to a double integral over d of partial of q with respect to x. So let's see, if I want to take the derivative of this with respect to x, notice I get y. And then I have to do minus the partial of p with respect to y, which is 0. So if I can evaluate this double integral, which actually looks fairly simple to do, then I'm good to go. Now, to do this, I'll probably have to figure out how I'm going to integrate over the region D. So I'll think about how I can define D. D is a region of x, y points where, well, maybe I could do something like this. X definitely goes from 0 to 1, and y definitely goes from 0, but goes up and hits this function here. I think this function would look like, let's see, it's got a negative slope and a positive y-intercept, so maybe 1 minus x I think there works perfectly. So now that I have my region D, setting up this double integral is pretty easy. So my double integral over D of y dA is definitely equal to the following. See, this is integrating with respect to y and then with respect to x. Of course, if I was to simplify or start to integrate this here, see, I'm going to get a 1/2 y squared, 0 to 1 minus x. If I was to simplify this out, I'm going to get a 1/2 1 minus x squared dx. This is going to be, I'll pull the 1/2 to the outside of the integral. Let's see here, I'm going to get an x squared minus a 2x plus a 1. So if I integrate this, I'm going to get a 1/2 1/3 x to the third minus an x squared plus an x, evaluate from 0 to 1. Of course, the 0 part's easy, so this is just going to be 1/2 and then, oops, 1/2, then I'm going to have 1/3 minus 1 plus 1. So of course that minus 1 plus 1 cancel out, and I'm left with 1/6. So the value of the original work integral is 1/6. Now this is actually really saving us a ridiculous amount of time. You should really take some time here to think about how complicated this question could have been if we didn't have Green's theorem. Because what I would have had to do is to find a parameterization for all 3 of these curves, and then calculate this integral 3 times, and then add all the results together. Like, I don't want to do this integral 3 times in a row, once along the bottom and the slant and then going on the vertical side. That's crazy. And if this was, a different shape other than a triangle, maybe it had more sides or things were more complicated to parameterize, it's terrible. But this simple double integral can really save us a lot of time. And it relates a lot of the ideas that we've talked about so far this semester. In the next video, we'll take a look at another couple examples just like this.